you for the introduction. It is a great honor to be here at this amazing conference. So my talk is about randomizing high-C data. We use the graph representation of high-C data and randomize it. What this means, we keep some graph properties unchanged, and the randomization is performed for result validation purposes of some topological studies. We have also used it ourselves, and I will tell you about our experience. But let me start with what exactly are the high-C graphs at all. So, you know, chromatin folds, and the high-C technology allows to capture those loci that are close spatially. So the high-C data is actually a list of interactions between loci. And it makes a lot of sense to represent this data as a graph where each node is a segment on the chromosome and each link is a high-C interaction. It makes sense because, well, the graph adds structure to the data and allows to use graph theory to study it. One issue with the high-C data is that between experiments the results are quite different. If you spot something in one data set, it might not be the case in the others because, well, for technical reasons, for technical artifacts. So in our recent study, we counted cliques in high-C graphs, and we had the hypothesis that they could be a good indicator of biological activity of chromatin hotspots and so on. And we needed to prove that, to check that, whether maybe that's just due to node degrees and the overall graph structure that those cliques just tend to form, you know? Or that would be the bad case, or the good case where, well, the cliques are there due to the biological activities. So we needed to construct a new graph, a graph that would be highly similar in terms of topology, but we would see whether some property would be preserved or not. So let me define now the requirements. So this here is a standard way to represent high-C data. It's a high-C matrix where each cell represents one contact. For instance, this one means that there is an interaction between 18th and the 57th segment. So our randomization needs to preserve the link count, the interaction count, and the node degrees, which is the most basic graph property. It also should be sufficiently different from the original graph. You know, it should be randomized after all. It means that all these dots must be somewhere else. How many of the interactions must change? Well, that depends on the parameter by user. And lastly, the link length distribution of high-C data in the resulting graph must remain similar. This means that between these green lines are all interactions of similar length. And we want there in the resulting graph to be just as many links as there were before. Unfortunately, that's too strong of a requirement, so we ask the distributions to be as similar as possible. Here I must mention one limitation that is important. In typical high-C data, there are almost all possible links along the diagonal. So there are almost no interaction that is not present in the data. So it is not possible to change, say, 90% of interactions when almost all of them are there. So what we do, we say, that's fine. We will consider most of them already changed. For instance, if between those green lines 80% of interactions are present, then we will only say that we need to swap 20% of them. Now, the algorithm idea. I will not go into details here because it's too technical, But basically, we modify the existing graph link by link. We choose two links and then swap their endpoints as seen in the animation. This obviously ensures that the node degrees of all nodes stay the same all the time. The link count does not change, but well, the link lengths do change. However, by choosing the links to swap in a smart way, we ensure that in the end, the link distribution is what we need. Now to the results. The most important result is it works on real data and works quite well. So we tested it on 3 data sets that were used in our previous study and some additional data sets from publicly available studies. All data sets were quite different. Some of them were PT high C, so promoter capture high C. Some of them were normal high C. The sizes of graphs were quite different, and the running times were reasonable on a normal laptop. So once we obtained the randomized graphs, we needed to compare them to the alternatives. However, none of the existing methods exist that preserve both link lengths and the node degrees. There are quite a few tools that randomize sequencing results of experiments, but well, they don't work with graphs, so we didn't consider them. There's one amazing tool that adds noise to data and that we managed to use for our randomization. So that tool adds 2 types of noises in different fractions. So one is the genomic distance noise that only preserves link lengths but not node degrees. And the other does the opposite, only preserves node degrees but not link lengths. So by combining them, they add noise, and then performing downsampling, a randomized dataset is made. We also compared it with a naive randomization that uses the same swapping technique but ignores link lengths, so it chooses links to swap randomly. So first, to check how well our algorithm performed, we utilized the 2-sample Kolmogorov-Smirnov test. It tells how similar 2 distributions are. So 0 means that distributions are totally the same and 1 not the same. So there were 2 typical scenarios for our results. Sometimes we managed to keep the distribution almost perfectly. Sometimes not so well, but still better than the alternatives. So there are several reasons for that. This scenario was either when graphs were smaller or when there were not so dense along the diagonal. So not all possible links were present in the graph. However, what's important is even in the larger graphs, our worked better than the alternatives. Next, we used the Hi-C-Rep tool to assess the reproducibility. It shows how similar 2 datasets actually are. One means the datasets are the same as per this tool, which is designed specifically for Hi-C data, and the other one is, So our method destroys the reproducibility much faster than the other methods. It is neither good nor bad. It's just how our method works. It was not the goal to preserve the reproducibility. However, this shows that our method destroys those things that the Hi-C-Rep is looking at. Now, back to our use case. So we wanted to check whether number of clicks drops after the randomization. And you can see that the number of clicks that is found in the dataset drops indeed. However, not as fast as with other techniques. It makes sense because our requirements are much stronger, and well, we ask to keep both node degrees and link lengths, whereas those other methods are not requiring that much. However, the point is it drops. So we managed to show that indeed the cliques in those datasets are not just due to those specific node degrees and link lengths. There must be some other biological reason for the huge number of cliques. That was the result of our other study. So to conclude everything, the algorithm that I presented indeed randomizes high-C graphs quite well. It keeps node degrees by design and also manages to keep link lengths quite decently, but well, not perfectly. Our method reduces the reproducibility score faster than any other randomization that we used. The randomization was used successfully in our other study to validate the results of a topological study, and we hope that it can be of use to some other studies as well. The method is implemented on GitHub, and it's freely available. It randomizes a list of links quite well. So all in all, it's a general purpose randomization technique. It's usable primarily for validating topology-related hypotheses in high-C data. With this, thank you so much for attention.
Okay, so are there any questions from the floor? Okay, now I have one to start first, actually. So I think this is a really interesting approach, like given what we've been discussing about having like null models or randomized models. So do you think your randomization method can help sort of give an assessment of whether some of the cliques that are identified are more interesting or that are likely to be something that like other biologists can study, for example?
Well, the method allows to generate a fine null model where nothing really happens. None of the biological things are really preserved, just the structure. So if the structure might be a reason for whatever findings a study finds, and then it's still there in the randomized data, that must mean that whatever someone found must be in a huge part due to the structure itself. So this tool will help to determine whether findings are due to topology or something else. So indeed, it can work as a null model quite well.
Okay, maybe I have another one actually. So essentially, one of the points that you made your conclusions is that it's actually this is also generalizable to other data types as well. So there's actually more graph-based models coming up looking at genetics or genomics, for example. Do you think your method of randomization will be like relevant in these areas as well, to look at rearrangements, for example?
We haven't tried to apply this algorithm to other data yet. However, if it is possible to assign nodes to some strings, to the chromosome with specific loci, and it makes sense to calculate the distances between those nodes, then it is applicable. It is not necessary to use it only on high-C data. However, on high-C data, it works the best because it's developed for it.
Okay, yeah, the question was there actually.
Oh, hi, thanks for the interesting talk. I have one comment. So for high-C interactions, it's like there are many algorithms to calculate the interaction from the sequencing data. Well, we work with high-C data for a little bit, and we figured that with different cutoff, you actually have kind of different interaction maps. So would your algorithm of randomization take the strength of the interaction or read depths and other things into consideration?
Thank you for the question. So in our other study, we used a graph where either interaction is in the graph or not in the graph. So
it's
it was
0, 1.
all
Yeah.
ones,
Okay.
yes. And we have not we have not applied this algorithm where counts are taken into consideration yet.
I see. Thank you.
Quick question. Super interesting study. I think you have shown that maybe at global level, this has some biological meaning. It's not random. But do you plan to work it on more local level, for example, subgraphs?
I think the question is whether this can be applied on subgraphs, for example, where essentially to look at very smaller.
Of course, yes, it can be. Why not?
Thank you.